Welcome. In this session in linear data analysis, we'll relate the score of a data vector with a hyperplane H to the probability that that data vector is in the positive half space of the hyperplane. Let's begin by reminding ourselves of our notation. We represented odds as a value S, and it was a real number that was strictly greater than 0 and there was no upper bound. From previous work, we represented the score as a value Z, and it was a real number, but there were no bounds on it. So it could range from minus infinity to plus infinity. Well, let's think, how could we map the score to the odds? Let's try mapping the odds to the score. So let's try to map, suppose we want to map a score, and we want to map a definite value of a score to a definite value of a function. So what do we want? So we want this to be invertible. That is, we want to be able to say, for a given odds, I want to produce a score, and we want to say, for a score, I want to find the odds. So it has to be invertible. So that means that it has to be smooth, and that means continuous, indifferentiable, and all the other things that go along with being smooth. And then it also has to be 1-to-1. And then for it to be invertible, it also has to be monotone. So it has to be, in some sense, strictly increasing. So an infinite number, infinite choice occurs. Let's put an exclamation because we don't usually get that, right? So now let's try graphing what we might mean. So what we mean here is that we have, suppose that we have our score here, and, sorry, we have our odds here, and we have our score here. And so what we want is, we want this to be invertible, smooth, 1-to-1, and monotone. Well, that means that it has to have this property, is that it has to be either concave up or concave down. And the usual choice in machine learning is to make it a concave down. So what I want is a function that has these properties. It asymptotically approaches, as it approaches 0, it asymptotically approaches minus infinity. As it goes to infinity, it goes up to infinity. That is, it never turns back down. That's part of the monotone. And if it turned down, it wouldn't be 1-to-1. And it also has to be smooth. So what of the infinite number of choices that we could make are appropriate? So what we'll do is we will choose a function that's very familiar to us. We could say that the logarithm function satisfies all of these. It's invertible within this domain. It's smooth, it's the 1-to-1, and it's monotone. So it fits all of the criteria. So what we'll do is we'll say that the score is the natural logarithm of the odds. And that allows us to infer that the odds are the exponential of the score. And so what we're able to do is we're able to start to relate odds and scores as this exponential. Now, how could we get the score? Well, let's recall from our familiar diagram what we do. What we do is we have our hyperplane H, and let's represent it as the unit normal n. And the unit is important because that means that if we take any vector u, we can find the signed distance of this. So from a hyperplane double-barreled H, what we get is the score of a new vector is the inner product of the normal and that new vector plus a bias scalar. And we would usually represent the normal as W and the bias as B. Now we'll represent the normal as N, and so it will be some other value A. So the score of a vector is the inner product of the unit normal with the vector plus a bias scalar that we'll call A. So now what we need to do is we need to figure out how do all of these relate to each other. Well, I know that the probability given odds is the score divided by 1 plus the score. And that implies, that if I don't want to use the score, I don't want to use the odds, I want to use the score. So now, to make this probability a function of the score instead of the odds, I substitute, everywhere I see S, I substitute e to the z. So that is e to the z over 1 plus e to the z. And that is one of the two common ways that we'll relate a score to a probability. The other way that we do it is, imagine that we multiply both sides by the top and the bottom by e to the minus z. So if I multiply the top by e to the minus z, e to the z times e to the minus z is 1. 1 plus e to the z times e to the minus z is e to the minus z plus 1. So that is equal to a 1 for the numerator, and the denominator is 1 plus e to the minus z. Let's make an observation about why the logarithm is a particularly good choice for the mapping between the odds and the score. Is, suppose that this is the score for our vector. Well, if that vector was exactly opposite of the hyperplane, we would want its score to be minus z. And we would want, if the probability of it being in the class here was p, then we would want the probability here to be 1 minus p. For example, if the probability was very close to 0.5, then we would want the probability of its opposite to be very close, of every vector that has the negative score to be very close to 0.5. If the score was very large and the probability was close to 1, then on the other side we will want the probability that it's in the positive half space to be nearly 0. And so if we use this, we have a consequence. So it's a consequence is that for this choice, the probability of something with a negative score is 1 minus the probability of it with the positive score. And that symmetry captures our notion of probability really, really well. So now let's work out the odds. So the odds of u in, I'll just say, positive half space of h. So now what we do is we take these values and we start to expand them, right? So our score of a vector was, we said that was n transpose u plus a. So that means the probability, so here we had the probability as a function of odds, here we have the probability as a function of score. Now I can write the probability as a function of the vector is actually, let's rewrite that slightly. Let's say that that's the probability of the vector given the normal and the bias scalar. And let's say that that is, now I take, let's take this form. So that is 1 over, and that is 1 plus e. Now I'll parenthesize it. So that is minus this. So that is e to the minus n transpose u plus a. And by observing that this here we're saying the probability is a function of u, and then parameters that we're giving are the unit normal and the bias scalar, is that we're now capturing everything that we need to perform this calculation. This has a name, so this is called the logistic function, and this function occurs quite often in statistical reasoning and in machine learning. So what we've done is we began with odds and scores, and then we had constraints on our mapping, and then the constraints on our mapping gave us a picture that reminded us that we have a function from long, long ago that meets all of those requirements. Then we work it through, and we get two lovely results. One is that it has a good interpretation of, there's a symmetry that's highly desirable, and we can also fairly easily calculate this in a computer program.